All right, so
You're barely halfway through the year. Like,
okay, so what's this nonsense that they've got in this book about the x minus a? So the linearization here, we can approximate the function by saying the original value plus, this is just dx, right? Or I mean dy, right? So they're writing down dy, what they're saying is dy equals f prime of a, in our book they call it c, same idea, right? Times x minus a, in our book it would have been x minus c. Okay, but think about the picture we drew, right? The picture that we drew looked like this, right? We had some value which we called c, we'll call it a, right? And let's say here's, that's a, sorry. And let's say here's x, okay? And then here's the tangent line that approximates the change in y. Okay, well we built the right triangle, and we called that dx, and we called this dy, right? And we just said, oh, this is just the slope of the curve, right? So we said that dy dx equals f prime of c, which would be f prime of a in this case, right? And so we said dy equals f prime of a times dx. Well, what's x minus a? Dx. Same thing, right? Okay? So that's all they're saying. It's just the actual, like for example, if we were doing like a real world problem, it'd be like the measured value minus the, plus with the error, right? Minus the predicted value, right? Does that make sense? Like if we measured something and we measured it to be 24 inches plus or minus 0.01 inches or something, right? Then 24 would be A, and then the value with the error included would be X, right? You see why it really is probably better. I mean, this is okay, but it really is probably better to think of that as being dx, though. It just matches the real world better, because dx looks like it's going to be the amount that we're changing something by, right? Does that make sense? But when you see that, so to answer to your question, when you see something like that, x minus a, just think of the picture. That's just dx. Okay? And you don't have to, you could do it with dx. I know when you look at their examples, they're going to say x minus a. That's where they get that. So then let's look at a problem like this, how about? So what are they wanting us to do here? If this is the function and a is -1 and they want the linearization, well, what really is the linearization?
Just the derivative of the original function times x plus 1.
Yeah, I mean it is just the slope of, I mean it's just the curve, right? Look at what their answer is on. Let's go back to ours that we were doing. Look at what their answer is. Find the linearization. Well, it's just the line, right? It's just the tangent line to the curve at that value of x. Nothing more. We did those probably 3 months ago, right? Right? So then all we're doing here, if I've got some function that's tangent to this curve at that value, well, what's my derivative? Because that's really just the slope of the tangent line, right? What is it?
Negative 12x minus 3.
Negative 12
X squared.
X squared minus 3. Okay. So then what is f prime of a?
negative 108, negative 111.
Negative 108 minus 3 more is negative 111. Yeah. Right? Okay. So that's the slope of the tangent line, right? and we need a point. Well, that's all right, so what's the point? So we get A is 3, what's f of A? So let's make that f of 3. What's f of 3, if that's our original function? What's it going to give us? 2754, negative 108 minus 9 plus 1 is minus 8, so 116?
Yeah.
Negative 116. So what's that tell us then? That tells us that the point of tangency is 3, negative 116, right? So then all we've got to do is go back to algebra 1. Y equals mx plus b. Well, okay, so there's a value of x and y that work, right? We know m is negative 111. We've just got to figure out what b is, right? So we'll evaluate this function at the point that we know and solve for b, right? So we get negative 116 equals negative 111 times 3 plus b. So what are we going to get? Negative 116 equals negative 333 plus b. So if I add 333 to both sides, I get 217. So y equals negative 111x plus 217. That's my answer, right? So all that is the linear model is just the tangent line. Okay? Make sense? Okay. So let's try. Okay, let's see how impressive your geek skills are. Try this one real quick. Try estimate what is 8.01 cubed approximately equal to. So don't look at your notes. Let's see if you can do this one. See if you can come up with an estimate. What's the equation that we'd always start with? The answer, y is equal
We can't
to,
even check our answers on the practice test.
what's that?
We can't check our answers on the practice test until the end.
Well, because it's a test, yeah.
Practice.
I know, but I hate that, but it's not my fault. I just want to make, if you want it to be like the test, the only way I can put pool the questions in the way they'll be pooled on the test is if I do it as a test. Math Excel doesn't allow me to do that if it's.
We need to like file some major complaints against
I
Math
agree.
Excel.
I agree.
Yeah, just hack it.
Yeah. So would 8.01 be C, or would it be, was that 8 of the C?
So what's always my approximation? It's going to be f of x plus delta x is always going to be approximated by what? F of x plus
F delta X.
plus dy, right?
Oh.
And we know what dy is. dy is just f prime of x dx, right? Okay. So if you just, and does that make sense? Think about that in terms of our picture, right? Right? Just think about that in terms of our picture, and you can't help but remember it. Right? If that's x, and this is x plus delta x, right? So then there's delta x, there's delta y, and what's our new y value going to be approximated by? Our original y value plus dy, right? Right? So this is the one thing that you kind of have to just remember from the picture. That's differentials in a nutshell, right there. That's it, right? So if we want to estimate something like this, then we just have to choose, and you want to really show off your geek skills, we just have to choose an appropriate value for x and dx and know what the function is. So what's x going to be for our problem up here? 8. What's dx?
0.01.
Okay. What's our function?
X cubed.
Kyle Tedder, please call extension 3804. Mr. Tedder,
Right.
3804.
So what's f prime of x then? It's easy.
2 to 3x.
What is it?
3x squared.
3x squared. Okay, so then this becomes pretty simple, right? So we're going to get f of, which is cubed, right? We're going to get 8 cubed plus f prime of x, which is 3 times 8 squared times,
0.01.
right? So what is 8 cubed?
512.
512, okay, plus, let's see, 8 squared is times 3, 192, times 0.01, 1.92, yeah, so you're gonna get 512 plus 1.92 is what, 513.92? Okay, let's just see how close we got.
That's pretty close.
Yeah, and that's just, I am so impressed with that. Isn't that cool?
Where'd you learn this anyways?
Stanford, that's what you're paying.
No, this is not.
This was like elementary school.
So look where we are. Whoops, what'd I do here?
Oh, nothing good. 8.01.
Oh, 1. Whoops, there we go.
Easy there.
Phew. I began to question everything I thought I knew.
What? No, okay.
Not bad. Not too shabby. You two can look smarter than you really are, just like I often do. So, all right. Try another one just to make sure. I just so want you to be able to just crank this out. And
In our head.
yeah, in your head, seriously. I think it's really cool to be able to do that. You can't.
Writing stuff.
You have to write it to get in your head.
No, you just start with it. in your
Okay,
head.
so let's try this one. Let's do, and it's easier if the radical ones are a little bit harder, but not too bad. Once you've done one, you just remember, it's the derivative of square root of x is just 1 over 2 radical x, right? That's kind of what you got to think about a little bit. But let's try one of those. Let's estimate what is the square root of, let's say, 15.85 is roughly equal to what? Here's the one, here's what I would say this. In my head, I would go 4 minus point oh 189 and get.
Yeah,
Okay, I'll talk you through it, because you can you're just do it in your head. If you're trying to really do this in your head, I'll show you. So that's gonna give you, what? That's gonna give you what, 3.9811.
That's pretty close to.
Okay, here's how you can do that though, right? So all you're doing is you're just doing the differential in your head, but then you gotta do a little bit of mental math, right? And then you could easily do 3.98 without even hardly thinking about it. You could do 3.98. But if you want to do the extra little bit, I'll show you how you can get that. 3 what I meant was, yeah, 3.98. Okay, so what's the function here? Square root of x. So f prime of x is what? Okay. X equals 16. Good. And dx equals negative. Negative 0.15, right? Just that much less than x, right? Okay. So then all we got to do is say our answer is approximately equal to f prime of 16, right, plus dx times f prime of x. So that's just going to be negative 0.15 divided by what? That's going to give us 1/8, right? See what I'm saying? Does that make sense? Okay, so what did I just do? Prime 16.
What? It's not.
That's supposed to be f of
Yeah.
16, right? Over 8. So we're going to end up with 4 minus 0.15/8 is the answer. So roughly, you could say, okay, 0.15/8 is approximately 0.02, right? And get it pretty good. But then you could even do that in your head. You could say, okay, well, it only goes in once. You could do this much math in your head if you just wanted to think for a few seconds and really get it out to a few places. You could say 8 goes into 15 once with 7 left over. 8 goes into 70 8 times with 8 left over. And 80 is almost 81, so 9 for the third digit, right? See what I'm saying? So you could make that 0.02 a 0.0189 without doing too much thinking.
I'm not sure about that math that you just did with the 8 going into 15 and then
8 goes
8
in
going
once,
into 80.
right?
But yeah.
So that's going to give you, think what that does. So that gives you 0.01 with 7 left over. 8 goes into 70 8 times with, I did just kind of screw up, didn't I?
Well, I don't even know what
With
you're doing.
6 left over. And so,
I
right,
I didn't know that.
No, it's 7. It's 7.
yeah, so it's, right, so it is, right, so you end up with 1, 8, and then instead at the end, that 9 was a little bit hokey, because then you'd get 6 left over from that, right? So I did kind of mess up a little bit. But it's always gonna get you a little bit closer, even if you mess up down here, you're still getting closer to the actual answer. So then 8 would go into 6, so it'd be about 8. So it'd be about, so that should have been 3.98 12.
Yeah, it should be 7.
Should be 7, but then I'm gonna say for the third one I'm not gonna keep carrying it. Then I'm just gonna round. See what I'm saying? Because 8 would go into 60, closer to 8 times than 7 times. So I would just take the 8.
No, it's
It's
the
not
same.
closer, it's the same
It's the
distance.
same distance.
Oh, you're right. It's the same distance. Oh, so either one, if you split here, yeah, either one would work. Yeah. Nice. And then the next one would be a 5. So you still would do any good to go.
Nice.
Right. Anyway, you get the idea? But really, you could have even, it would have been pretty impressive just to do the first one, say 15/8 is 0.02, right? Subtract 0.02, you're still getting really close. And you're getting really close in like 5 seconds. Right? I just think that's so cool. Okay.
That's pretty good.
Yeah, isn't that, we even learned something that tricky. That's, yeah. Okay. One more I want to go through, though. We went
Too
through,
much tricky.
let's go through, there's one other kind that I think is really cool that we haven't done yet. Let's look at something like,
So you take, yeah. After that's and then find the derivative, and then plug in that, so you take it, and you plug it back into the derivative equation. There's maybe 3, and then prime there.
okay, let's look at 31, for example.
Seriously, that's the size. We're kissing you organized. Come on.
Sometimes tough to know.
All right, so
Pretty fun, so.
let's just forget about part A. Let's just do part B. So let's estimate the maximum allowable percent error in measuring the side if the error in computing the area, the propagated error, cannot exceed 2.5%. So this is a truer kind of problem that you would do as an engineer, right? If you've got to figure out, based on what the next person in the chain up of this engineering process is telling you, okay, you're engineering these milled cubes, is that what we're doing? Squares, and we can accept an error in the area of more than 2.5%.
How do you
So-
figure that part out?
Say it again?
How do you figure your percent error?
That's what I'm gonna figure out.
That's calculus on their side.
How did they figure that out?
Yeah.
Well, they figured it out maybe, I don't know, let's just say hypothetically that these things are gonna be used to create masks for spraying ink on something, and so you're gonna be printing these squares, and who knows what the down, but they've done some kind of research that says their optical sensors need it to be, you know what I mean, something like that.
But would they use calculus too?
Oh, most likely they would use calculus, yeah, probably calculus in the next step up form, which would be differential equations. Okay. So what are we gonna do here then? This is the same kind of thing we've been doing, right? We've gotta come up with our approximate change in area, right, as a function, related to area. Okay. So what is the area function that we're dealing with here?
That's why.
X,
Oh.
well, no, area is
X squared.
x squared, okay. So we're dealing with an area where a of x equals x squared, right? Okay, so what's a prime of x?
2x.
I like that. That's good.
Okay, and what is so we're saying that x equals
12.
12. Right? Okay, so then they're saying that the maximum allowable percent error in measuring area cannot exceed 2.5%. So that's not, they're not comparing dx over x. They're saying that dA over A has to be less than or equal to that, right? Does that make sense? Does everybody see that these statements are equivalent? That whole thing right there corresponds to the math statement, math equation, or inequality in this case. dA over A must be less than or equal to 0.025, right? Because this says percent error, right? Or relative error, but we'll just write it as a percent. They wrote it as 2.5%, which is a decimal, would just be 0.025, right?
Yeah.
Okay, we good with that? Okay, so then all we got to do is say, well, here, we've got some pretty simple expressions for A and well, dA would be what? dA is just going to be what? If A prime is 2x, then dA is
12 times 0.025.
2x minus x.
it's just going to be 2x dx. All that is the differential form of the derivative, right? This is really just equal to dA dx, right? A prime. So we're just going to write that derivative in differential form where we multiply that dx, move it over to the other side, right? Okay, and that's literally just a disconnected from anything we're doing here in calculus. That's just a new way of writing a derivative, right? We just make sure that we multiply both sides by dx when we're done. Okay, so then if we put this into our formula here, what's this give us? 2x dx over x squared has to be less than or equal to 0.025. Okay, so we could cancel an x, and what's the only unknown here then if we cancel those x's? Dx. That's it, right? See what I'm saying? And look how cool this is. What they really want here is they want the maximum allowable percent error. So what's that really going to look like? Dx is the measurement error in x, but the percent error in measuring x would be what? Would be dx over x, right? When they ask for something like this, the allowable percent error measuring the side, well, that's saying percent error is a relative error, right? That's going to be dx compared to x, right? So they want to know dx over x has to be less than or equal to what, right? What's the allowable percent measuring error, right, for x? Well, look right there. There's a dx over x right there. Just divide by 2, yeah. So dx over x then has to be less than or equal to 0.0125. So 1.25%. See how that works?
It's really confusing when it starts introducing other variables, like a, when they change it to a instead of y, it confuses me.
Well, okay, so y is just, now let's think about that for a sec. So y is just our generic dependent variable, right? But when we start getting into real situations that are where the function means something, then it makes sense, instead of calling it f of x, which is equal to y, we're going to call it something like a of x, because it's an area function.
Yeah, it makes sense to just confuse us first.
Okay?